Hey, good morning, everybody. All right, so in today's lecture, what we're going to do is we are going to do a two-part lecture series on what are known as C++ containers. You're already familiar with one C++ container, which is standard vector. And the whole idea of a C++ container is that it implements algorithms or data structures to be able to implement, so you can use these to implement advanced ideas. Now, we're just going to briefly discuss what it is that these containers do. We're not going to go into a lot of detail as to what's going on underneath. I'm just going to explain just enough so you can understand which data structure or which container in particular you might want to use in a specific situation, with the objective that by the time we're done with these two lectures, so today and then Monday, you have an idea of how you can use these C++ libraries to try to solve advanced problems when you, if you want to, for example, if you want to use a project later in your career here at Notre Dame, or if you're in industry and you're using C++, you can use this to make some decisions about effective design. Okay, so the first one I would like to teach you about is called standard pair. And the whole idea of standard pair is that it has two private objects and they're both templated. And this allows you to be able to put pieces of information together that are logical to put in pairs. So the way it works is you would have standard pair, and then you will template it with two different types. And the way you will access an element in there is, since it has two private members, the way you would access it is dot first to get the first element, and then dot second to get the second element. I do want to point out that you are not putting parentheses after these. Okay? You're actually able to access these by going just dot first and dot second. So since we are able to access these members of the class, what do we know about them based on our knowledge of classes? If we were trying to construct our own pair class, and we have first and second, and we would want the user to be able to access them just like this, where it would be dot first instead of having to have some sort of accessor method. What do we know about? Yes, they're public members, absolutely right. So first and second are public members. And so here I have an example. We could have a student, we could have some sort of counter, and there's all kinds of different ways in which we can implement standard pair. And there's one example, the first example I'm going to show you is the quadratic formula. Negative b minus the square root of b squared plus 4ac over 2a. And when we have the quadratic formula, there are two potential answers. So if we were trying to come up with a function that said, all right, give me the answer to the quadratic formula, if we were just returning a double, it wouldn't be very effective, because this would mean that we would have to return two different values, and that wouldn't be possible. So another way we might approach this is to call two doubles by reference and then do the same object twice. Or what we can do with the standard pair is that we can say, let's do a standard pair of doubles, and let's calculate the first one, and then calculate the second one, and then store the first one as a positive result, and the second one as a negative result. Does that make sense? So we can use standard pair to reduce some coding complexity. And so first, what I'd like to do is I'd like to show you some code that I have here to actually do this. So what I'm doing is I'm returning a standard pair object that's templated. The first object and, the first member and the second member are both doubles. And then I read in three values, double A, double B, and double C. And then what I do is I calculate the inside square root. I create a local pair, and then solutions dot first is going to be negative b plus square root of inside square root divided by 2a, and solutions dot second is minus b is minus the square root, and that quantity is divided by 2a. And so what are the two things that I need to do in order to make sure that that square root function works? So to start combining concepts we've been learning this whole semester, there's two things that I need to do. It involves library and compilation. Yes. Yep, we have to include CMath, so that's one of them. And so, Ian, did you have another? Okay, so does anybody remember what we have to do in the make file in order to make this math library work in C and C++? Anybody remember? Yes. Dash LM, absolutely right. Let me just bring this up so I can get solutions from the people on the chat. Yes, dash LM. We have to add the dash LM to our compiler flags in order to be able to do these mathematical operations. And so here, this allows us to be able to do square root. And so now we have both values, and then we can return the solutions. In order to print solution, I'm going to call the standard pair by reference, and then I'm going to print out first and second. So this is an example of the standard pair of the benefit of call by, one of the benefits of call by reference. The other benefit being that it's easier to code. So we don't have to dereference a pointer, so we don't have to do arrow first and arrow second, but also because standard pair can be templated to anything, it can be a huge class like student. That means that if we're only passing a pointer to the function, we are significantly reducing the memory that we use because we don't have to make another copy of that standard pair. And so here we're just printing them out. And in main, what I've done is I've created two quadratic functions where a is 2, b is 4.1, and c is negative 3.7, and I print the solution. And I do the same thing with a second quadratic equation with 2, 4.1, and 3.7. And so when I compile it, I would run that. So let's, I want to ask you a question from math knowledge. Does anybody see any issue with the values that I put in to one of those two solution quadratic functions? Yes. Absolutely right. We're going to get a negative argument in the square root. And so what's going to happen is when I compile this and I make quad pair, the second result is going to give me no legal value because I try to make a negative, put in a negative value in the square root. Very good. So this means that I would want to come up with another way to be able to determine whether or not I have a correct value. So if we're trying to think of what do I need to know for a quadratic formula solution? I need to know whether or not the inputs that have been put in are valid. I need to know the positive result, and I need to know the negative result. So does anybody have any ideas as to what we could do with a standard pair to solve this? Any ideas? Take a wild guess. There's no shame. Everybody stay up way too late to last night watching the results. Yeah. You could make a complex type. That's one type of way of doing this, but that's not quite what I'm looking for. I want to actually see if we have a valid result or not. Yes. Very good. That's exactly what I'm looking for. We could have one variable be a Boolean to indicate whether or not it's true. And then the second element in the standard pair could be another standard pair. So I can pair it with a bool to give me a result. So that's exactly what we're going to do. And so what I'd like to do is I'd like to show you quad pair 2. And this time, what I have is I have a standard pair where the values that are templated are a Boolean, and then the second one is the standard pair of doubles. And so when we construct a standard pair, it's just like we've been doing. You call the default constructor. And in this case, if we called a default constructor on doubles, it would set it equal to 0. So this means that when we can call our default constructor and do whatever we want. So here I do the same thing. I get the inside square root in the denominator, and then I create the local object, which is the standard pair of bool and another standard pair. And then I have these two cases. I say if inside square root is less than 0 or the denominator is equal to 0, then I set solutions.first equal to false. So therefore it would just be false, and then we use the default constructors. It's 0 and 0, but it doesn't matter because we've already indicated that we do not have a valid way of calculating this without using complex numbers. Otherwise, what I'm going to do is I'm going to set solutions first to true. And then what I'm going to do is I say solution second, and that's going to be the second element is the pair. So it'll be solutions dot second dot first. Does everybody see that? Solutions dot second dot first will give me the positive result, and then solutions dot second gives me the negative result. So what I'm going to want to do is when I check it, I'll first check the Boolean. If it's true, then I'll print out the negative and positive result. Otherwise, what I'm going to do is if it's false, I'm going to say we don't have a valid result. And that's what's going to happen here in print solution. In print solution, I say if it's true, I'm going to print the values out. And again, I'm going to say solution.second, which gives me the standard pair, dot first. And then the second is going to be solution.second. Otherwise, if solution first is false, I'll just print invalid result. Does anybody have any questions on that before I compile? Yeah.
Sir, can you go over again how you determine in the first place how to set the Boolean?
Sure. Okay, so we're going to go back up here. And so this is a kind of a review of the quadratic formula. So either we have two cases where we can't represent the number without using complex values in the computing device. So we're going all the way back to the first lecture. We have computing devices, and we can only represent certain things. We cannot represent the square root of a negative number. Right? So my first case here that I have highlighted is inside square root, and that's b squared minus 4ac. If that value is negative, that means we would have to have a square root of a negative number in order for us to be able to, we have a square root of a negative number, which means we can't calculate the result. The other time is when we have, since the quadratic formula is negative b plus or minus the square root of b squared minus 4ac, and all of that is divided by 2a. If we have 2 times a, and a is 0, that means we would be dividing by 0, and we can't represent that inside the system either. So either the square root, inside square root is less than 0, which violates one way, or the denominator is equal to 0, in which case we can't represent it. In those two scenarios, I set that solutions.first, that bool, that's when I set it to false. Awesome. Are there any other questions? All right, let me check the chat as well. All right, so what I would like to do is I'm going to run. Yeah, oh yeah, what's up? Yep. Correct. We don't need to touch it, and here's why. So I was alluding to this a little earlier, but let me provide a little more clarity. So remember when I was talking about how when standard pair has the default constructor and it has these two members that are double, and it will call the default constructors on those. What's going to happen is that double for in the standard pair, it will construct both of the doubles on the heap, and it will set them both to 0, right? Since the first value is false, it does not matter what they are. So we can just leave those alone. It's kind of like most of you are Doublys or have worked with electronic circuits. You're familiar with the idea of don't care? Okay, so in circuit, how many of you have no idea what I'm talking about? Oh, okay. All right, so this is, hey, I'm going to give you a brief preview of your future. So in electronic circuits, in fact, for homework 9, you'll encounter one of these, but I did. It's basically, if there's a certain input, it doesn't matter what that input is because it doesn't have any contribution to the output. That's the short version of it. So in an AND gate, so let me drop an AND gate here. So the idea of AND logic, I have A, B, and Y is equal to A and B. So the idea of a don't care is if A is equal to 0, everybody see that? That means the answer is guaranteed to be 0 no matter what, which means I don't care, which is often represented by just an X crossing it out. I don't care what the answer is. So in this case, we're going to apply this idea of don't care to what's going on here. When that value is false, we do not care what the pair of doubles are. It could be infinity, we could put in any number we want, it doesn't matter. Did that address your question? Okay, I'm glad I designed homework 9, assuming that some students didn't know that. Okay, so let me run quad pair 2, and it's going to do the same thing, except this time, it's going to print out the valid values, but here, instead of giving us minus NaN for negative infinity, it's going to say invalid result because we've caught it. So we have a standard pair, and one of the values is the standard pair itself. Does that make sense? Does that make sense? Okay, awesome. Okay, so there's quad pair, printed results. But wait, what happened here? We know what happened here. The next container I'd like to introduce you to is the C++ representation of a data structure that you're familiar with. I've introduced you to singly linked lists, and C++ has a singly linked list container. It calls it forward list. And you have to include, include forward list to actually run it. So the whole idea is it's all the elements underneath are linked in nodes, just as we've learned. And so to iterate through, we'd have to traverse all of them. We don't have direct access, right? So we can use this, and I've included a link if you want to look up all the little nuances of how to use forward lists in the future. You're welcome to refer to this link, and that will help you figure out what kind of ways that you can play around with this and use it to your advantage. In a singly linked list, you want to typically use it when memory is limited and you want to convey a lot of information. So the advantage is you've got to keep information on the next element only. You're going to have what I'm going to say, big O of 1 in insert. And the reason I'm going to say that, and in fact, let me click on the link just to kind of give you some perspective. Okay, here we go. The only way to insert into a singly linked list is push front. Okay, remember we did insert where it went through and inserted on the back. We also used inheritance and polymorphism to do a sorted insert. Now, the thing is, with the singly linked list, here it's going to say, I only want to insert at the front. So it's going to do that case that we drew up where they would say the head node is being pointed to, right? And then we created a new temporary node. We had the head node point here, and then we had this one point there. So that's the only way to insert into the C++ singly linked list. Now, they're setting up for a data structure that we're going to learn later in this lecture called a stack. But for right now, that's important to know because it's a limitation on how you can use it. So the drawbacks, the elements are in a strict linear sequence, no sorting or arranging capability. But you know how to do that because you've written one sorted. So one of the benefits of learning classes and kind of what you've learned fundamentally is that there are times when the C++ standard template library might not do what you need it to do. I'm limited in memory. I only want to store the exact amount of information that I want it to be dynamic. A inspector uses twice as much memory underneath. That's bad for me. Let me just use the singly linked list. Oh, I can't sort it. Well, now I know how to construct a class. I know inheritance and polymorphism. I can make this work for me rather easily. Okay, so that's what I was just saying. All right, so here is how you would construct one. You have to include the library, and you need to template it. So here we have a template within. Now you can put in several elements at once. So flist1.assign, I'm initially putting in 1, 2, and 3. And the reason why you want to use an assign is because it'll put it in that specific order. Now, if I want to insert using push front for 4, where do you think that 4 is going to end up in this list that I've drawn up on the screen? Yep. Very good. So it's going to go here because it's going to become the new head node. So now pop front is that version of delete that we have covered. Except it's only going to have, so the head node is currently pointing at 4. What's going on underneath is that it'll say, all right, it's next, and then it will free that specific node. So that just does, that's pop front. And this is a good example, and C++ containers are a good example of this concept I've been talking about of abstraction. If you're able to implement the C++ singly linked list, and it does precisely what you need it to do, you don't have to worry about writing your own class. You can use this, and the people who wrote the C++ standard template library will do the work for you. The question ultimately becomes, when you get out of class, is does it do what I need it to do? And if not, then I write my own class stuff. All right, does everybody understand about what's going on here for right now? Okay, so the next thing I'd like to go over is a unique way of doing an iterator in C++ when you're using the container. So what I would like to, I'm going to circle this particular piece of code here. And the whole idea is that it seeks to simplify the iteration if you intend on iterating through every single element in the container. That make sense so far? So here is what this means. If I'm iterating through a whole singly linked list, I have a list of ints in this case. Each element in that node, each element contains an integer. And what's going to happen is if I have this linked list that we drew up 4, 1, 2, and then 3, what this piece of code is going to do is it's going to call the integer in that specific node by reference and return it. And then you can do anything you want with that integer. So if you call A inside that loop, it's going to treat it as though we're dealing with this specific integer. So it can be used to perform operations on the linked list. I don't know it can be a little confusing. So does anybody have any questions? All right, so let me show you some code here. And this is make forward list. And here, first let me show you in main what I'm doing. So I've created a singly linked list of integers, and I've created a singly linked list of strings. So just like I was doing before with classes, I want to test to make sure my templates work with different types of inputs here. So then I've created, just like I showed you in the slides, 1, 2, and 3. And then I'm going to call print values, which I'll show you in a moment. And then I push front 4 and 5, and I print the values again. And then I say Irish go, then I pop front, and then I print the values again. So now what I want to do is I want to show you this print values, because this is where the iterator comes into play. So first, I'm just saying the values are, and it's going to iterate through all the elements in the singly linked list, and then it's going to print out that element. So here it's templated with a call by reference, and the current element is A. Then it's going to just print it out, and then after it's done, it'll just print everything. It'll print the end line. So what we're going to do is we're going to see these lists at different stages after inserts and removals. So when I run make forward list, what's going to happen is initially I used the sign to do 1, 2, and 3, and then I did push front 4, and then push front 5. So we see 5, 4, 1, 2, and 3. Then I did go Irish, and then what you'll see down here is I called from the forward list integer, I called pop front. So 5 was initially at the front, and then I removed it, and it's now 4. So that's why we get this specific result. All right, does anybody have any questions before I continue? The next thing I'd like to show you is this file iterator.cpp, where we're going to go into a little more detail about how some of these work. So I have the forward list, and here it's just the exact same piece of code. When I go through here, I want to show you what's known as the auto keyword. The auto keyword creates a pointer to a specific node. So if you want to iterate through this particular container, and you don't want to go through everything. So here I want to say I want to go to the end, right? Well, let's say I want to stop at a specific value, right? So what I would do is I would say auto forward pointer. I would say star forward pointer equals we'll say it does not equal 3. So what I'm doing here is, because auto creates a pointer to a specific node, when I dereference it in the C++ library, what it does is that is giving me the value. When we created our singly linked list class, we would go through and we would call some sort of accessor method. So just like the ampersand with call by reference is being used to try to simplify some of the coding complexity, in C++, what this is doing here is it's saying, all right, give me the value inside the specific forward pointer. So this whole line of code is saying, all right, give me a pointer to the initial element in the singly linked list. Then we're going to keep going while the value inside of that particular node is not 3. And then it's going to increment the pointer, which is saying that I'm going to move to the next element in the singly linked list. So this piece of code right here that I've highlighted, that's the equivalent of us going cur equals cur next. right? So that's what's going on there. Now inside, what I have is if forward pointer is equal to 7, so I've dereferenced it, then I say forward pointer is equal to 1842. So now what's going to happen is when I print it again, it'll initially have 1, 2, 7, 3, and 4. But I can do the same thing here and say it'll be 1, 2, 1842, 3, and 4. And then I have, I'm sorry, went a little too far. Then I have this second loop where now I'm iterating through everything. And I say int val is equal to 3, then I say int val is equal to 77. What is going on here is that this is creating a pointer, and this is call by reference. So this is supposed to be simple, a little more complex here. But this gives me the benefit of being able to say, I want to stop at a specific point. Whereas with this other notation, we're doing int ampersand, int val colon forward list. This goes through all of the elements. So if you want to go through all the elements, then this is the notation. If you need to stop at a certain condition, then you should use the auto keyword to do so. Does anybody have any questions about this? So what I'm going to do is I initialize the singly linked list. Then I'm going to update if I find it at 7. Then I'm going to update if I find it at 3. Then I'm going to push front, and then I'm going to print the values out. So it should print out 0, 1, 2, 1842, 77, and then 4. For the standard vector, what I'm going to do is I'm going to have a standard vector of strings here, but I can iterate through that as well in the same way. So it says, let's go Irish. Then I say, well, if A is equal to let's, then I say, here we. So it's going to say, here we go Irish. And then I'll push back, here we go Irish. Here we go on the end. So it's going to print out, here we go Irish, here we go. So while it's taking its thinking. So the initial elements are 1, 2, 7, 3, and 4. We use that first iterator to find 1842, the auto keyword. We use the second one to find 77. Then when I use the standard vector with the iterator, said let's go Irish. And then I'd say if we found let's, then we replaced it with here we go. So that's how we were able to access the element in the vector using that iterator. And then I use push back onto the vector to do here we go. So does everybody see how that works? Let me check again to see we don't have any questions in the chat. So here the standard forward list and vector have begin and end. So this is where I'm describing it in the slide, and that returns a pointer to the node. And so the keyword auto permits declaration of a STL iterator. So that's what I was doing in that specific code. I was declaring an iterator that points to the nodes in that specific, in this case, the forward list. And then I had to dereference it in order to be able to get those values, which we saw here in the code. Same thing, C++ has a simple way to iterate through. And I've shown you this now where you do the template. It's a call by reference with the value A, colon, the list. And here's all the code I just showed you, and there's the output. Right. So does anybody have any questions on iterators or singly linked lists before I get into this idea of building? All right, so a doubly linked list is just like a singly linked list, except what's going on here is each node has a next and a previous pointer. So one of the drawbacks of the singly linked list is I can only go in one direction, right? With a doubly linked list, what this will allow me to do is I can traverse in any direction and I know where I came from and where I can go. So the trade-offs are more flexibility in programming, but the drawback is I have more memory because I need to use more pointers. The library for the doubly linked list is just list. So we have forward underscore list and list. And again, I've included the link for the list. It's here in the implementation for the C++ standard template library. So just like a singly linked list, we have no direct access. So we have to either iterate through using the auto keyword or with our simplified smart iterator. But it also has big O of 1 insert. Now here's the good thing about doubly linked lists. It has a head pointer, but it also contains a tail pointer, which means I can insert at the end of the doubly linked list, because what I'll have is I will have a tail pointer pointing at a node, and its next pointer is pointing at null, and its previous pointer is pointing at a value. So what I would do is I would create a new node, and tail, I would have this one point here, I would update tail, and then I'd have its previous point there. That allows me to be able to insert on the front and the back of the singly linked list. I'm sorry, doubly linked list. So I'm able to use it for other tasks. And this is kind of setting up for what we're going to call a queue in Monday's lecture. All right, so does anybody have any, I'm sorry, let me go back. Does anybody have any questions on this before I continue? All right, so just like with a singly linked list, we have a method called assign, where I'm able to put in the elements in a specific order. And then I can call push front or push back to put the elements in here. So with assign, we have 1, 2, and 3. Push front is going to put 4 at the front, and push back will put 8 on the back like so. Pop front would remove the element at the front of the list, and then pop back will remove the element at the end of the list. There are several advanced algorithms for being able to remove from the front of and the back of a list only become very beneficial. Okay, so let me show you. So here I have the list library, right? Print values, I'm iterating through the exact same way. So it abstracts a lot of that complexity for you. And now let me go to main. So notice how I have const unsigned int, the 6-fingered man. So how many of you have seen the print movie, The Princess Bride? I hope that's everybody. If not, I might have to just make next Wednesday's lecture watching that. All right, so what I'm going to do is I'm going to use a doubly linked list to try to put in words from Inigo Montoya's famous line. So I have count's going to be the 6-fingered man. I've created a doubly linked list, standard string, and it's just going to say is. So I'm initially going to push front name. So it's going to be name is. And I'm going to print the values as I go. I'm going to push back and push front. So I've got Inigo, my, and Montoya. And then I'm going to use the iterator and replace. So here, so when it finds Montoya, it'll say, Montoya, you killed my grandfather. Oops, we made a mistake. Let's fix this again. So I'm going to pop back. I'm going to remove Montoya, you killed my grandfather. I say, Montoya, you killed my father, prepare to die. And then we're going to print it again. And I'll say, push front. I'll say, bonjour. Oops, that's wrong. We'll print it out. And we'll say, hello. And now that we're here, I'm going to print out and say, Inigo is ready to confront the 6-fingered man. We're
We're going to iterate through 6 times, and it'll go all the way through. So if I run this, I'll say make clean, clear, make an ego. And it starts out, we're pushing everything on the front and the back. So we have is, we push front, it says name. We push back Inigo, we push my, so it says my name is Inigo. Then we got Montoya. We've replaced the element at the end that we realized was wrong. So now it says hello, it says my name is Inigo Montoya. You killed my father, prepare to die. We say bonjour, my name is Inigo Montoya, you killed my father. That's wrong. That's not how we work. So we update it because he's a Spaniard. So we say hello. And then we're at the final scene at the end where he's chasing down the 6-fingered man. He just keeps repeating it. I guess this room likes the Princess Bride more than the Notre Dame fight song, I guess. So that's just a kind of a cute little example of how we can use push front and push back to get some strings and things into a doubly linked list. So does anybody have any questions on doubly linked lists? All right, so the last thing the last type of C++ container that I would like to describe for you today is what's known as a stack. And a stack is what's known as a last in, first out data structure. So what's going on is, let's say I want to put in several elements. Move this over. And we're going to call this a push. If a stack is empty, I can say that I'm going to put 1, and then I can put in 5, and then 2. So the way it's working is, I can only access the top element in the stack at any given moment. So that means if I'm going to pop it off, that means I would have to remove 2, and then I would be able to access 5. You can't access any other element in the stack like that. So let me give you a thought question here. So I inserted 1, then 5, and then 2. So if I have 1, and then 5, and then 2, what kind of container do you think that behavior reflects, other than the stack? What does that look like? Singly linked list, very good. So we're just putting an insert in there, right? So we're going to push front, and then if we can pop, we're going to call pop front. So the reason why in the singly linked list it has accessors for push front and pop front is because they're using that as the underneath approach to building what's called a stack. So this allows us to be able to insert and remove everything in big O of one time, because all we have, no matter how many elements are in the stack or the singly linked list, we would be able to update the head node and free the old node in the exact same amount of time. Does that make sense? So that's why we call it constant time, which is why we call it big O of 1. So here is what we're going to do. We'll skip over that slide. I forgot to delete it. So a standard stack, we have to include the stack library. It has the default constructor. And the way it's going to work is you push the elements in, and then you pop them. And we also, and I think it's going to be on the next slide, we have a method called top, which allows me to be able to read the element at the top of the stack. So here I would say 4, it would be 8. If I called top, it would give me a copy of that value. And then pop would remove 8, and then pop would remove 4. Does that make sense? So there's top, and then we can also determine how many elements are in the stack
and whether or not it's empty. So I want to go over two types of problems, and I'll give you an idea of how stacks can be beneficial. So this is a common interview question, and it says design a straw stack and its relationships which support max and min operations. So that's kind of complicated because we can't just iterate through the stack. We can only access the element at the top of the stack. And the other thing is we want to be able to have it run in big O of 1 time. And then it says use big O of n space complexes. So that means if we multiply it by 2 or 3, it's still in big O of n. Does that make sense? So what this is going to, this is something if you wanted to go in a lot more detail about data structures, about the theory, what's going to happen is we're going to create 3 stacks, and every time we encounter a new minimum, we're going to put a minimum onto the min stack, and every time we encounter a maximum, we're going to put a value onto the max stack. And so that's what that slide says. Okay. So what's going to happen is that let's say I have 2. Well, 2 is the only value in there, so it's simultaneously the minimum and maximum. And if I put in 8, I'm putting in 8 into the stack, but 8 is also bigger than the previous max. So we put it in there. We get 7, it's neither the maximum or minimum, so we can put that in there. 8, we're putting that in there because if I remove 8 from that stack, I would still have an 8 in there. So I want to make sure that I could still do this. And then I would go through the entire thing. And then what could happen is if I pop 6 off, I should be able to say at any given time that the minimum is 1 and the maximum is 8. If I remove 1, now I know that the minimum is 2 and the maximum is 8. If I remove 2, that still works because 2 is at the bottom. If I remove 8, I still have 2 and 8. I remove 7, 8, and at the end, I have 2. And so this is where I will start Monday's lecture. Actually, I'll quickly go over the Towers of Hanoi on Friday to kind of wrap this up. But what I have here is I have a class. In this class, I have 3 stacks. So I call it max stack. And then privately, I have 3 stacks, data, min stack, and max stack. And then I have a long unsigned int, which we briefly discussed earlier, that size t is a long unsigned integer. But each of those represent the size, the amount of elements in the stack at any given moment. When I construct this max stack, I have 3 elements, data, max data, and min data. So I'm calling the constructors on the C++ containers. From here, I say if it's empty, you just return if the data is empty. If I only have a minimum value and I don't have a maximum value, there will never be an instance where that will be the case, because if I have one element, like one case 2, then 2 is also the maximum and the minimum at any given moment. Here I have an accessor method top, which gives me the top element of the data. I have a push method. And what push is going to do is it will automatically push onto the data stack and increment the data size. And I know there's 1 minute left. If max data is empty or the value is greater or equal to the max data, then I'm going to push onto that max data stack and increment that size. We do the same thing for min, where it's less than or equal to, or if it's empty. For pop, I will always remove the element off the top, but that will be last. I'll do that down here. If data.top is equal to max data.top, then I just print out that we found a max. I'm removing the max data and subtract that size and do the same thing. And then max, this will give me the maximum value. I just remove the top of that stack. I do that, return with a call by reference and const. And then I do the same thing with min. In stacktest.cpp, what I'm doing is I'm going to read in inputs, And then hold on, let me go down to main. So I'm going to seed a random number generator. Oh, have we covered random numbers in this class? No? Oh, we have. Okay. Okay. I thought I was losing my mind. All right. So I seeded a random number generator, and then I create the stack, and then I push a bunch of random numbers. So I read in, I'm going to say this number of elements I want to put in and a range. So if I put in 12 elements and from 0 to 1,000, it will randomly generate results. So let me say make stack test. Let's compile it. And what's going to ask me to do, enter the values. So I'm going to say 13 different values. I'm going to say the range can be from 0 to 999. And now what's going to happen is we say elements pushed onto the stack. So it generates all these 929, 0, 18, 568, 296, all the way out here. And then I'm going to remove all the elements. And I know that's the maximum's 996. And then I just keep going. And in this case, it was just all the way down here until we get to the bottom. Let me run this again. I'll do 10 and 1,000. And here we have a few more maximum and minimum values, but we're able to access them in big all at one time. All right, does anybody have any questions? All right, in that case, you are dismissed, and I will see you on Friday for our very last Lab Friday. We've made it.